Ever wonder why an apple falls from the tree? Why does it not go up or sideways or simply hover in the air? Welcome to the world of gravity, the invisible force that keeps us grounded, both physically and astronomically. Imagine an apple hanging from a tree. What's pulling it down? That's gravity, an unseen force that pulls every object with mass towards every other object. The larger the mass, the stronger the gravitational pull. It's like a cosmic game of tug-of-war where every object is a player. Now, let's touch on Newton's law of universal gravitation. It was Sir Isaac Newton who figured out how gravity works. He put it like this: every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Sounds complex, right? But it's simpler than you think. When we say directly proportional to the product of their masses, it means the more massive two objects are, the stronger the gravitational pull between them. Imagine two sumo wrestlers versus two kittens. Who do you think will exert a greater force of attraction? And when we say inversely proportional to the square of the distance, it means the farther apart two objects are, the weaker the gravitational pull. Consider the sun's gravity. It pulls us much harder than the moon, but it's because it's much closer. Next, we have acceleration due to gravity, represented by the letter g. This value tells us how much an object speeds up as it falls towards the Earth due to gravity. On Earth's surface at sea level, g is about 9.8 meters per second squared. This means every object, regardless of its mass, falls towards the Earth at this rate. So, a feather and a bowling ball, dropped from the same height, will hit the ground at the same time, assuming there's no air resistance. But here's a twist. G isn't always a constant 9.8. It can vary depending on a few factors. As you ascend higher above Earth's surface, the distance to its center increases, and your distance from its gravitational pull also increases. This means G gets slightly smaller. Astronauts on the International Space Station, for instance, experience a G of about 9.0 meters per second squared. Earth isn't perfectly round. It bulges slightly at the equator. This means G is a bit higher at the poles than at the equator. Dense underground rocks or other massive objects can create tiny local variations in G. So, to recap, gravity is an unseen force that pulls all objects with mass. Newton's law of universal gravitation explains how gravity works. G is the acceleration due to gravity on Earth, which is about 9.8 meters per second squared. G can vary slightly depending on altitude, latitude, and local variations. That's all for today's lesson on gravity. Next time you see an apple fall from a tree, you'll know exactly why it's happening. Thanks for tuning in.